So this is the code that controls the Arduino device within your circuit. Firstly, we can see library includes up here. The first include is the Bluefruit. Bluefruit is a library created by Adafruit to control all their Bluetooth communication. There'll be a lot of reference to this library in future where it simply references functions that they created. After that is the .star library. This is specific to this project simply because I used .star LEDs. If you use the NeoPixel range, then you'll have to include the NeoPixel library instead. After that is the definitions. Firstly is numpixels. This simply defines the number of LEDs that you've utilized in the project. After that is the data pin and clock pin definitions. They simply define the pins that you used on the board to connect the board to the LEDs. After that, it's simply a variable that describes the dot star strip. So in future, when you reference strip, it knows exactly which pins and how many LEDs there are to control. Beyond that is the simple initiation of Bluetooth UART. After that, we've got some functions that communicate with the second file that we'll discuss in a little bit. They mostly handle things to do with the incoming communication and the packets received. After that, we've got this predefined color that's created using RGB. It's simply a pale blue color that should be the first color that is shown on initialization. After that is just a variable that holds the current color. As you can see, it currently utilizes pale blue, but is frequently changed in the code future on. Beyond that, we've got the time tracking variables that utilize millis. Millis just records the current millisecond clock on the device. See how that's used further down. After that is the strength variable. This is a variable that is utilized to determine the current brightness of the LEDs based on the time that's changed. After that is the speed factor. This can be changed either in the code now or via the application device. The speed factor is multiplied by 100 milliseconds. So right now, 4 multiplied by 100 milliseconds will be about 400 milliseconds. So the larger the speed factor, the longer the animation will take. After that, we've just got some variables that can store the individual RGB components of a color. They're utilized further down in the code. Finally, we define the individual states of the animation. Because we're replicating a very specific animation available to view in the game, I had to figure out exactly which LEDs should be lit at any current time. Eventually, I figured that there were 3 states, and you can see which LEDs should be lit per state as they are contained within the arrays. Beyond that, we simply create a variable that can hold a packet buffer. Then is setup. Here you can see a lot of lines that include this serial. Serial is simply to do with monitoring the code and how it's going. There's a tool called the serial monitor. So whenever you see anything that's serial.print, it's played in that monitor. So it's mainly used for debugging. What's important here are the lines that don't include serial, such as bluefruit.begin here. Most of the code here is to do with Adafruit's own library. I'm confident that they do work, but again, you might need to explore their code themselves to see exactly what it does. Down here we've got the advertisement code. Again, it's utilizing a lot of the Bluefruit library. However, I do understand that this is how the Arduino device itself advertises itself for availability to mobile devices or anything that is looking for any peripherals. Below this, we start to see some of the custom functions. As you can see, we've got red, green, blue functions here. They simply return the specific RGB values of a hex code that defines color. After that, we've got darken and brighten functions. If we start with darken, you can see that it takes a hex color and the strength variable, and it utilizes them to pull out the individual RGB colors and then multiply them by a percentage. This percentage is calculated by the strength value. So as you can see, red is taken from max color and it's divided by 100 to produce a percentage scale, and then it's multiplied. This is done for red, green, and blue, and then they're put back together to get a new color. The individual components of the color have to be removed and individually manipulated, because if you simply try to manipulate the overall color, rather than darkening that shade of red, you might end up with a completely different color. The same is true for brighten. The only difference is strength is immediately multiplied onto the current color component rather than it being negated from 100 first. Next, we have functions that control the different stages of the animation. All it really does is it carries the strength, so it knows what to brighten, but it knows which sets to brighten or darken, or completely set to 0. As you can see in this first animation, it brightens the first set and darkens the second set while leaving it brightens the first set and darkens the third set whilst leaving the second set completely black. It does this by simply setting the strip color of the specific LEDs, and the color is defined by the brighten function previously explained. Similarly with the second and third animations, the second set simply brightens the second set and darkens the first whilst leaving the third set black. Third set brightens the third, darkens the second, and leaves the first set black. Here is the animation update function. This is the function that determines which of those 3 previous functions should be utilized. This function starts by taking the current time. It takes that current time and checks against the previously updated animation, or the time of the previously updated animation. By doing that, it can understand how much time has occurred since. It knows how much time has occurred since. It can figure out which step of the animation it should be playing. As visible here, it takes the current time, negates the previous time, and then checks to see whether that time is less than the speed factor times 100 milliseconds. For example, if speed factor was set to 1, it would simply be 100 milliseconds. So if only 68 milliseconds had passed, it would decide the first step of the animation should be visible. Once it understands that, it calculates the strength value of the LEDs, so just how bright the LEDs should be right at that time. This is again done based on the time that has passed. So it simply takes the current time minuses the previous time and divides that by the speed factor. which is then passed to that first animation function. Beyond that, we've got the conditions for the second animation to play, which is simply the second third of the animation's time window. As is visible here, it has to be more than the speed factor times 100, but less than the speed factor times 200. Again, strength is calculated, however this time that first speed factor window is negated, simply so that we can get a similar strength value regardless of when we get it. And again, for the third animation, it simply must be more than speed factor times 200 and less than speed factor times 300. If the time is greater than any of these, then simply reset previous millis to be the current millis. This indicates that the animation has run through all 3 stages and is ready to repeat fresh. After that, we've just got a small function that is utilized further down. This function simply is involved with communication, and it calls a function that is available in the second file. Right, now we've reached the main loop. This loop is constantly repeated in the device. First thing it does, it sets the strip brightness to 1/5 of the available strength. So regardless of the strength variable that we utilize, this just sets the max limit to 1/5. This is to save on charge and stops the device from overheating. Also, as these LEDs are just so powerful, setting them to max brightness is dangerous when the LEDs are so close to the wearer's eyes. After that, we've got a function that calls the previously explained animation update function. So within this loop, it pretty much at the start of the loop, it's constantly checking at what stage of the animation it should be at. Beyond that, once it's checked which stage of the animation it should be displaying, it checks for any communication from the mobile device. Once it's done that, once it's checked for communication and received something back, it checks what kind of communication it received. Here you can see that if the first character in the packet is a C, it knows it is reading a color value. So it pulls the red, green, blue values from that packet and sets the current color, which was defined at the start of the code, to the color given. If the first character is an S, it knows that it's defining the speed of the animation, so it simply pulls that from the packet and sets the speed factor to this value. After that, if the first character in the packet is an A, it knows it's receiving accelerometer data. So again, it pulls the XYZ values from the packet, and then we manipulate them. Firstly, we reduce these coordinates by a factor of 10, so we can get a value that is usually between 1 and 0. Confirm that they are between 1 and 0 by simply setting anything above 1 to the maximum that is 1. And finally, we multiply that value by 255, which is the max RGB values for each color, meaning that if the phone is held in such a position that X is 1, then red is the primarily displayed color. After red, green, and blue have been defined, the current color is set to this combination. After that, if M is defined, if M is in the first character of the packet, then it knows to utilize the magnetometer. This hasn't been converted into any color manipulation currently. Beyond that is the gyroscope. So if again the first character is in G, then it can pull the X, Y, Z values. Unlike the accelerometer, we get different kind of values as this deal with rotational acceleration. Here we've simply said that if the coordinate value is greater than 3, then change to a predefined color. This was the easiest way to manipulate the gyroscope, as 3 was a good value found in testing, where it was simple enough to get a value at least of 3 where it wasn't too sensitive. Anything below 3 was too sensitive. Anything greater than 3 wasn't sensitive enough. So here you can see if X is greater than 3, so if you swing your phone upwards, it changes to red. If you swing your phone downwards, it turns off. Swing your phone, or if you rotate the phone, then it's a value, it's green. And if you swing the phone left or right, it's blue. Again, you can see that these colors are then utilized in changing the current color. Lastly, in this file is the quaternion, which again, if the first value in the packet is Q, it knows to utilize that. However, those haven't been translated into colors. After that, we have the second file. The second file mainly utilizes much of the predefined code from Adafruit. However, there have been some small changes. What was mainly changed was how the code listens and waits for a communication from the mobile device. One of the largest challenges with this code was understanding how this an Arduino cannot multi-thread, meaning that any kind of delay causes the machine to wait unnecessarily. So previously, whilst the device waited for a timeout on the communication, it used a while loop. This while loop would lock the device away from the animation code, meaning that it couldn't animate the LEDs whilst waiting for a communication. So what I did was remove that while loop and utilize millis to figure out the current time. So rather than wait unnecessarily within this loop, it simply checks whether it should time out or not, and then quickly moves back to the animation and returns. So here you can see we take the current time, then it checks against a load of conditions where it utilizes the current time against the previous time, and if that is less than the timeout, then it can continue. If it's more than the timeout, then it has timed out and it needs to reset. If you wish to understand this code in further depth, I would recommend searching the Adafruit libraries and their websites. However, as I understand it, it's mainly to do with reading the packet that has been received and printing that information to the serial monitor, or simply to figure out exactly what's inside. It's not too complicated. These are the files associated with the Android application. Since Adafruit are an open source company, these were originally downloaded from their Git. Not many changes were made to this application. Only small modifications were done to prove to myself that I did in fact understand the application enough to make some functional changes. What I decided to do was produce a speed variable bar that could send a value that could be utilized as the speed factor in the Arduino. To start with, this is the fragment layout of the color picker wheel. I added a variable bar here with the highlighted code. All it really does is define the layout, the text view, and the seek bar. This then correlates to the controller color picker fragment.java. As you can see, is not too long an individual file, and all I've really done here is amongst all the code that defines what every button does in terms of the color picker and the send button, I've inserted information regarding the seek bar. So you've got the normal things like just the UI and finding the right text view and color views. But what's important here is the seek bar. As you can see, I've defined the seek bar and said that it's using the speed bar ID from the previous window. And the seek bar simply listens for any changes done to the bar. If something is changed, then it fires the onSend speed components function. All that's left down here is again that onSend speed component is defined, and that's done. That then is followed up here in controller fragment.java, where you can see that it's basically building the packet that is to be sent. It starts with an S, just like how any of the other packets sent, they all start with a letter that defines what that command is. So in this case, it's an S for speed. And then it builds the buffer, the length required. And after that, it just puts the data in the packet and sends it. Not that much else, as these all these functions here, like send CRC data, right there, are functions pre-built into the application. So rather than build an entire new function to send data, it was easy just to use what was utilized. So yeah, it just sends this string, which starts with S, and then that speed value is appended on the end. After that, it packages it up and sends it off. That's all there is to this app.